Legendre Polynomial. In this video, we will use Taylor Maclaurin SERIESSUM to generate the expansion of the Legendre Polynomial. We also use COMBINA, ARRAYFORMULA, data validation, and LINEST Polynomial Regression. So we define the Legendre Polynomial as the summation of a times x minus 1 over 2 to the power k, where a is equal to COMBINA n minus k plus 1 comma k times COMBINA n plus 1 comma k, and the value k is from 0 to n, and we assign our n using data validation from 0 to 10. So these are the values of our n. So here we have n ranging from 0 to 10, and our k will be is from 0 to n, so equal to sequence n plus 1 comma 1 1 column starting from 0 incremented by 1. So at n equals 0, our k is 0. N equals 1, our k value is 0 1. N equals 2, k value 0 1 2. K equals 3, our k value 0 1 2 3. Now we enter the Taylor Maclaurin SERIESSUM expansion, which is array formula. SERIESSUM 1 minus or x, that's x minus 1, so x minus 1 over 2 raised to the power starting from 0 incremented by 1, and the coefficients will be this range. So here we have the trend line equation and the trend line, where we use the trend line equation to generate the Legendre polynomial. And we can continue with the value of a, which is the coefficient, which is equal to our formula. Start with the first term, COMBINA n, COMBINA n minus k plus 1 comma k. Sure. If this is empty, this should be 0. So we will correct this. So if k is empty, and it should be 0. Otherwise, calculate. Now, if k is empty, this should be 0. We have fixed the problem. Next, continue with the second term, which is again COMBINA. So times COMBINA, and that will be n plus 1 and plus 1 comma k, n plus 1 comma k. Okay. So here we have the Legendre polynomial. Start from 0. At n equals 0, our Legendre polynomial is y equals 1. So y equals 1. At n equals 1, Legendre polynomial y equals x. So y equals 1x. At n equals 2, our Legendre polynomial is minus 0.5 plus 1.5 x squared. So minus 0.5 plus 1.5 x squared. at n equals 3. Legendre polynomial y equals minus 1.5x plus 2.5x cubed minus 1.5x plus 2.5x cubed. Legendre polynomial at n equals 4, or it is y equals 0.375 minus 3.75x squared plus 4.375x to the fourth. So that's 0.375 minus 3.75x squared plus 4.37 times 10 at x to the fourth. At n equals 5, our Legendre polynomial y equals 1.875x minus 8.75x cubed plus 7.875x to the fifth. So that's 1.88 minus 8.75x cubed plus 7.88x to the fifth. At n equals 6, our Legendre polynomial y equals minus 0.3125 plus 6.56x squared minus 19.7x to the fourth plus 14.4x to the sixth. So that's minus 3.313 plus 6.56x squared and minus 19.7 times x to the fourth and 14.4x to the sixth. At n equals 7, Legendre polynomial y equals minus 2.18x or 2.19x minus 19.7x cubed, 19.7x cubed, negative 43 minus 43.31 x to the fifth minus 43.3 x to the fifth, 26.8 x to the seventh, 26.8 x to the seventh. N equals 8. Legendre polynomial y equals 0.273 minus 9.84x squared minus 9.84x squared plus 54 x to the fourth, 54.1 x to the fourth, 93.8 x to the sixth, 93.8 x to the sixth, 50.3 x to the seventh, x to the 8, 50.3 x to the 8. At n equals 9, our Legendre polynomial y equals 2.46x, 2.46x minus 36x cubed minus 36.1x cubed plus 140x to the fifth plus 141x to the fifth. So this is 141x to the fifth plus 201x to the seventh, 201x to the seventh, and 94.9 or 95x to the ninth, 95x to the ninth. At n equals 10, our Legendre polynomial y equals minus 0.246 plus 13.53x squared minus 117x to the fourth plus 351x to the or 352x to the sixth minus 427x to the eighth plus 180x to the tenth. This completes the use of Taylor Maclaurin series sum to generate the expansion of Legendre polynomial and the LINEST polynomial regression to generate the trend line of the Legendre polynomial.